Physics is the most fundamental and all-inclusive of the sciences. Everything that living things can do can be understood in terms of the jigglings and wigglings of atoms, is a quote from Richard Feynman in the third lecture in his famous series. This reductionist point of view is pretty common today, and we can see it in everything from ex-KCD comics to Sabine Hossenfelder's new book, Existential Physics. If we could just re-express organisms, economies, and social interactions at the atomic level, and apply the laws of physics with a big enough computer, we'd know everything that happens at the higher levels. And in that sense, all the interesting stuff in the universe only really happens at the bottom. At least, that's what the physicists tell us. And unfortunately for them, they're wrong. The way we study complex systems, like those in biology, simply can't be reduced to physics. I know that sounds pretty radical, but hear me out and I'll explain. In 1687, Isaac Newton published his Principia Mathematica, which would go on to lay the foundations of modern physics. The picture we get of matter from Newton is that it doesn't do anything by itself. That's his first law. If it does happen to move in a particular way, then we know that it must be under the influence of some kind of external force. But when we look at the biological world, matter seems to move by itself all the time. In this beautiful film of the development of the Alpine newt, Jan van Eycken shows us just how non-Newtonian biology appears. Cells fold in on themselves, and atoms stop bumping around randomly and start swimming together as one little tadpole. As Dennis Walsh puts it more poetically, if Newton's laws lay down the rules by which matter conducts itself, organisms flout them flagrantly. Of course, I'm not saying that there are any new forces involved in the development of living systems, like the vitalists claimed, just that we might need to take a different perspective compared to the Newtonian paradigm. One different idea we can use is the concept of top-down causation. Instead of saying that the jigglings of atoms alone cause the newt to move, which is the standard bottom-up perspective, we also need to look at the reverse direction. The atoms are only moving in the way that they are because they happen to be in a newt. This isn't even that radical. The atoms in this GIF that I keep showing are moving in the way that they are because they are bounded by this square box. If the box were a different shape or missing one of its sides, the atoms would behave differently. This is very simple top-down causation. If we ignore all these top-down causes, we'll miss so much of the interesting stuff that happens in our universe. Any form of higher-level organization will be invisible to us, because at the scale of atoms alone, we can't see anything really. The organism disappears entirely. Sure, if we wanted to build a giant supercomputer to simulate features of the biological world at the level of atoms, we might be able to make some predictions about where collections of atoms would end up. But we wouldn't be able to understand much about biology at all. Take this example from one of my university lecturers, Christian Camilleri. Say we wanted to understand what caused World War I. If we start our explanation with, so you see there were a bunch of atoms over here that assembled themselves into a 3D structure we call a bullet, we're not going to get very far. We clearly need higher-level historical explanations like imperialism, nationalism, the system of alliances, and so on. This happens to be the right perspective for generating knowledge in this case, and it can't be reduced to physics without making our explanations meaningless. In the same way, the self-organizing characteristics of biology can't be reduced to physics without our view of the organism becoming so diluted that it hardly makes much sense. Because of the limitations of any one scientific perspective, Michaela Massimi calls for a multi-perspectival approach for generating knowledge. We're like blind men touching an elephant, and no single perspective of ours will ever be able to give us a complete picture of the universe, not even physics. We need all of the sciences working with each other to put together a full picture. Mathematical models of biochemistry and biophysics certainly are insightful, there's no doubt about that, but we should be cautious of thinking that we'll ever be able to explain the whole organism with them, because organisms also break down the classical methods of computing and mathematical modelling that we have today. The modern computer was first conceived by Alan Turing, who initially described them as universal computing machines. Today, we call them universal Turing machines, and everything that your phone or computer can do can also be done by a universal Turing machine. So they serve as a catch-all way of understanding computation. The structure of a Turing machine is pretty simple. It takes its input on a tape of ones and zeros. Its hardware is a machine head that can slide along the tape and rewrite the numbers on it. And its software is an algorithm that tells the head what to do. This picture maps onto physics quite well, where the laws seem to be static over time, so we can reasonably call them the software of the particular system we're studying. But if we try to map this picture onto the organism, we run into trouble, because the quote-unquote software of organisms changes over time. For instance, the way an embryo behaves is very different to how an adult behaves. Not only that, but the way an embryo changes to develop into an adult is somehow self-derived. So it's not a normal Turing machine, but more like one that builds itself. One of the founders of computing, John von Neumann, actually designed a theoretical machine that could construct itself, known as a universal constructor. But up until today, no one has managed to build one. The closest we've gotten are 3D printers that can print most of their parts, like this one called RepRap. The problem is, you still need humans like these guys to put the parts together. I'm sure I don't have to tell you, but your parents didn't have to arrange all your internal organs while you were developing in the womb. You managed to work that out all by yourself. So organisms seem to be the only real von Neumann constructors that we know to date. This has even been shown quite nicely by Janny Hoffmeier, who has mapped von Neumann's original design onto the biological cell, albeit with some important modifications inspired by the work of Robert Rosen. The simple observation that organisms make themselves is nothing new and goes back to philosopher Immanuel Kant in the 18th century. Kant highlighted that the parts of the organism are only there because they are somehow related to the whole organism. Your neurons are there because you need to think, and you have mitochondria because your cells and really your whole body needs energy. This is top-down causation back again. Of course, the whole organism only exists because it's made up of parts. So together, we have this weird kind of circular relationship that seems to be fundamental to life and completely foreign to physics. I can't understate how strange this kind of causation is. It's something much deeper than a recursive function or a simple feedback loop. If we want to use a metaphor to computing, it would not only be programmer and programmed, but also writer of the language the programmer is using and builder of the computer. If we want a more mathematical metaphor, it would be like an equation that could write itself by adding in new terms and even new ways of mixing terms together with new axioms. Either way, that is something we just don't know how to deal with. Somehow, cause and effect are entirely wrapped up inside the organism in a way in which we haven't even begun to understand. But one key consequence that we can get from this is that the organism has a sense of agency that puts it well beyond the domain of physics. In classical physical systems, objects are always bound by laws, and their possibilities are inherently limited, because all the possible states of a system can always be described beforehand by what physicists call phase space. But in biology, we again run into a problem. We can't define all the possible states of a system ahead of time. Say I gave you this screwdriver. You could use it to tighten a screw, poke someone, pick your nose, stir your coffee, teach a class. The possibilities are literally endless. Or more precisely, we should say that they're indefinite. We can't pre-state them in advance. But if we can't define a phase space for the organism, then we have no hope of coming up with a universal law, because no matter what subset of possibilities we choose to describe with our law, we'll always leave something out that is possible for the organism to reach. Every model of the organism will always be incomplete. So the future that organisms have is open in the deepest possible way. They're creative enough to construct futures that we could never imagine with any algorithm, equation, or anything else. They're agents in control of their own fates, not objects limited by the phase spaces of differential equations. And thus, the tools of physics are too limited to capture the whole organism. Science isn't about reducing everything to physics or fundamental laws of nature. Physics is just one very particular tool we apes have invented to understand reality. It's a useful tool, no doubt, but it's not the most fundamental or the most inclusive or the most important. It's just one perspective. To even begin to understand the way the universe works with our limited brains, we need as many good perspectives as we can get. We want our toolbox to be full of different, insightful ways to see the world, not just a hammer that reduces everything to the jigglings and wigglings of atoms. Thanks so much for watching. This is the third video in a series on why biology is not mechanistic like physics. If you want to watch the first part on the history of the debate, you can click here. And if you want to watch the second video on why cells aren't machines, you can click here.